welcome back. Now I'm going to do a problem. I'm going to illustrate the concept of dispersion. Why when white light goes through rain, it disperses and it creates what's known as a rainbow, right? And when white light goes through a prism, it also disperses, separates out, right? And it also creates a rainbow. Isaac Newton was one of the first ones to investigate this concept, and it was a very, very important concept, and it showed that white light was composed of different wavelengths of light. So let's take a triangular prism here. Let's assume that it's an equilateral 60-degree angle on all sides, 60-degree angle. And let's say a beam of white light comes from the side here with an initial angle of 55 degrees, right, from the normal. And then what's going to happen when it enters into the glass medium, it's going to split up, it's going to disperse. Why? Because the index of refraction of that material, the n value, depends on the wavelength of light, right? So the index of refraction of red is different than the index of refraction of violet, right? So you have your visible spectrum, Roy G. Biv, red, orange, yellow, green, indigo, blue, violet, right? Red light, you look at a data table online, and depending on the material of the glass, for red light of wavelength 640 nanometers, it says, 640 nanometers, the index of refraction is 1.509, 1.509, and for violet of wavelength 434 nanometers, okay, the index of refraction is going to be 1.521, 1.521. So basically you get a spectrum depending on the wavelength of the light beam, right? So red will refract less, which means it will bend less when it goes from air to glass than violet does, right? So what would be the refraction angle of the red? Okay, so when it goes from air to glass, so air is going to be just 1. So sine of this one is going to be 55 degrees. The index of refraction of glass for red would be 1.509. Sine of theta r. So you're going to have here, okay, so that's going to be my red light, 32.7, like this, 32 degrees from the normal, 32.877, okay. My blue and violets are going to bend more, right? So they're going to look something like this, right? So then their refracted angle is going to be smaller because the violet is slowing down more when it's going from air to glass, and because it's slowing down more, it's bending more. So then it's going to be here sine of 55, then I'm going to put 521, 1.521 sine of theta r, okay, 586 degrees. So you see, it's slightly less than this one. So then what's going to happen? Well, then when they go and they meet the other side of the glass, right? So let's just concentrate on the red for now. 32.877 for the red, right? What is this angle going to be? Well, this is 90 degrees, right? So 90 minus 32.877, 90 minus 32.877, that's going to be 57.123, right? This piece is going to be 57.123. Then from there I can add this. You see this forms a triangle, and I can find out what angle that is, right? So 57.123 plus 60, right? And then subtract 180 degrees, this one right here, right? Then finally, in order to calculate this one, the theta incident on the other side of the triangle, right? So this one here was the 32.877, right? So then I want to eventually find this one right here, right? So I found this one, I added it, I subtracted it from 180, I got 62, then I'm going to subtract 62 from 90. So that's the incident angle of the red beam of light on the other side of the prism, right? So then when it comes out, it's going to bend away from the normal, right? It's going to look like this, right? The blue one is going to bend away from the normal. It looks like this, right? So this, we want to find out this theta refracted. Okay? So that's going to be the theta R for the red. Okay? 43 degrees from that normal line, right? So now let's do the same thing with the blue. So what's going to happen to the blue? The blue's angle was a tiny bit smaller, 32.586. So the blue is going to come like this, and then refract outwards, and then we're going to calculate the theta refracted of the blue, and then subtract that from the theta refracted of the red. This gives us the dispersion angle. The delta theta is known as the dispersion angle, right, of the beam of light. And that's kind of how you create the rainbow too. If this was water, the light would go through water, and then it would disperse, and it would give you the different rainbow colors, right? It would be red, then orange, and then yellow, then green, then blue, then indigo, then violet. So it'd be the whole spectrum of the wavelengths, right? 86. From there, let's calculate that angle. So it's 90 minus 32.586. That gives me 57.414. 57.414. Then let me add that to 60. And then subtract 180. 62.586. So this one is slightly less. 62.586. Then subtract that from 90. You get 27.414. Okay? So this angle, instead of 27.123, is 27.414 for the violet, right? So a slightly larger angle, right? Which makes sense because since this is steeper like this, it comes and hits this side of the glass at a larger angle. So then we're going to use the index of refraction of the violet, 1.521, sine of 27.414, that's equal to sine of theta r. So same step that I did here. So the theta r for the violet is 44.451. You see, it's a steeper angle. And then this one is 43.469. If you subtract that, this gives you the dispersion angle of the ray of light. So it depends, of course, on the index of refraction for red, for that material. The index of refraction of violet, it depends on the prism's angle, the 60 degrees, right? And it also depends on the initial angle that the beam of light was coming, right? If the initial angle of the beam of light was steeper like this, right? If this angle was smaller, let's say 40 degrees, then it would bend more, and then the dispersion angle would be more, right? So the more like this the beam of light comes, it comes straight like this, right? So the dispersion angle is going to be less. So it depends on the parameters of the angles of the triangle and the initial incident angle of the beam of light, right? So let's subtract that, delta theta, and this is known as dispersion angle. Okay, so now you can kind of understand where dispersion comes from, the dependence of the index of refraction on the wavelength of the light, and how to calculate that dispersion angle depending on what kind of triangle you have and the initial incident angle of the beam. Thank you very much.